calculate the appropriate transformer size for a hairdressing training facility, we need to follow a few key steps. Firstly, we need to calculate the total load. We have 300 training stations. Each station has two 120-volt, 20-amp duplex receptacles. Each station has its own dedicated circuit. To find the total current, we multiply the number of stations by the amperage per station. This gives us 300 stations multiplied by 20 amps, which equals 6,000 amps. Secondly, we determine the transformer capacity. Transformer capacity in kVA, kilovolt amps, is calculated using the formula current times voltage divided by 1000. Thirdly, we apply a demand factor. A demand factor accounts for the fact that not all stations will be operating at the maximum capacity simultaneously. For a training facility, we can assume a demand factor of 0.6. This means we estimate that only 60% of the stations will be in use at any one time. To get the revised transformer capacity, we multiply the transformer capacity by the demand factor. So, revised kVA equals 6,000 amps times 120 volts divided by 1000, multiplied by 0.6. This gives us a revised kVA of 432. Now, we need to select transformers. To meet the revised transformer capacity of 432 kVA, we could install three 150 kVA transformers. Or we could use two 200 kVA transformers and one 40 kVA transformer. Remember, the 8 new 120/208 volt panels will be used to distribute the power from the transformers to the training stations. A separate demand factor calculation may be needed for the building service panels if they supply other loads besides the training stations. Let's delve into the calculation of total load a bit further. The calculation of the total load is critical as it forms the basis for all subsequent steps. Given that each of the 300 training stations is equipped with two 120-volt, 20-amp duplex receptacles, and each station is on a dedicated circuit, it's important to understand what this means in practical terms. A 20-amp circuit at 120 volts theoretically provides 2400 volt amps. However, the National Electrical Code, (ONEC), typically requires that continuous loads are not loaded to more than 80% of the circuit rating. This means that a 20-amp circuit should not continuously supply more than 16 amps or 1920 volt amps. In the context of a hairdressing training facility, it's reasonable to assume that the tools and equipment used at each station, such as hair dryers, curling irons, and other styling appliances, may operate for extended periods. Therefore, these should be considered continuous loads. Given this consideration, using the full 20-amp capacity for calculation might lead to undersizing the transformers. It might be prudent to apply the 80% rule from the outset. Instead of calculating based on 20 amps per station, use 16 amps. This would provide a more realistic estimate of the actual load. Using 16 amps per station, the total current would be 300 stations times 16 amps, equaling 4,800 amps. This lower value will result in a more conservative and potentially safer transformer size. Now, regarding the transformer capacity calculation, the formula kVA equals current times voltage divided by 1000 is a standard formula, but it's essential to understand its basis. kVA represents the apparent power, which is the total power delivered by the transformer. It's the vector sum of the real power, measured in kilowatts or kW, and the reactive power, measured in kilovolt amps reactive or kVAR. In a purely resistive load, such as heating elements, all the power is real power. In inductive loads, such as motors, some of the power is reactive. Hairdressing equipment typically includes both resistive and inductive components, so it's essential to account for both. The formula assumes a balanced three-phase system. It's also essential to ensure that the voltage used in the calculation is the line-to-neutral voltage. In this case, the 120 volts is the correct value. However, if dealing with a three-phase system, it's essential to use the appropriate line-to-line or line-to-neutral voltage, depending on the configuration of the load. As for the demand factor, The application of a demand factor is a crucial step in sizing transformers economically. A demand factor of 0.6 suggests that on average, only 60% of the training stations will be operating at their maximum capacity simultaneously. This factor can vary significantly depending on the specific operating characteristics of the facility. For instance, if the training schedule is tightly controlled, with staggered start times and breaks, the demand factor might be lower. Conversely, if all stations are typically in use concurrently for extended periods, the demand factor might be higher. To accurately determine the demand factor, it would be beneficial to consult with the facility operators. Review historical usage data from similar facilities, or conduct a load study during a typical training session. This will provide empirical evidence to support the chosen demand factor. It's also crucial to consider potential future expansion or changes in operating procedures. Selecting a demand factor that is too low could result in the transformers being undersized, leading to voltage drops, overheating, and premature failure. In addition to the demand factor, another factor to consider is the growth factor. The growth factor accounts for potential increases in load due to future expansion or changes in the type of equipment used. For example, if the facility plans to add more training stations or if they anticipate using more power-hungry equipment in the future, it's essential to factor this into the transformer sizing calculations. A typical growth factor might be 1.25, meaning that the transformer capacity is increased by 25% to accommodate future growth. Now, after applying the demand factor, the revised kVA is calculated to be 432 kVA based on the initial 6000 amps, or 345.6 kVA if we adjust the amperage to 4800 amps applying the 80% continuous load rule. This figure represents the minimum transformer capacity required to meet the anticipated load. When selecting transformers, it's essential to choose standard sizes that are readily available and cost-effective. Transformers are typically available in standard kVA ratings such as 75 kVA, 112.5 kVA, 150 kVA, 225 kVA, 300 kVA, and so on. In this case, to meet the 432 kVA requirement, you could opt for three 150 kVA transformers, providing a total capacity of 450 kVA. Alternatively, you could use two 225 kVA transformers, giving a total capacity of 450 kVA. If using the more conservative number of 345.6 kVA, two 150 kVA transformers and one 75 kVA transformer will suffice. The choice between these options depends on factors such as cost, availability, space constraints, and future expansion plans. Selecting larger transformers provides additional capacity for future growth. It can also improve the overall efficiency and reliability of the system. However, it also increases the initial cost and may require more space. When choosing transformers, it's essential to consider the transformer's impedance. Transformer impedance is a measure of its opposition to the flow of alternating current. It's typically expressed as a percentage of the transformer's kVA rating. Higher impedance transformers tend to limit fault currents, which can protect downstream equipment from damage. However, they also tend to have higher voltage drops under load. Lower impedance transformers provide better voltage regulation, but they may require larger overcurrent protection devices to handle potential fault currents. Choice of impedance depends on the specific characteristics of the electrical system, the coordination of overcurrent protection devices. In addition to the transformer kVA rating and impedance, it's essential to consider other factors when selecting transformers. These factors include the transformer's voltage rating, insulation class, cooling method, and enclosure type. The voltage rating must match the voltage of the incoming power supply and the voltage required by the loads. The insulation class determines the maximum operating temperature of the transformer. The cooling method can be either self-cooled, fan-cooled, or liquid-cooled, depending on the transformer size and operating environment. The enclosure type protects the transformer from environmental factors such as dust, moisture, and corrosion. Finally, remember that the 8 new 120/208 volt panels will be used to distribute the power from the transformers to the training stations. These panels must be sized appropriately to handle the anticipated load. They must be equipped with the correct overcurrent protection devices. A separate demand factor calculation may be required for the building service panels if they supply other loads besides the training stations. If the building service panels supply only the training stations, then the demand factor applied to the transformers can also be applied to the building service panels. However, if the building service panels also supply other loads such as lighting, HVAC, and general purpose receptacles, then a separate demand factor calculation must be performed. This calculation should take into account the diversity of the loads and their operating characteristics. This calculation is more involved. It typically requires a detailed load analysis and consultation with a qualified electrical engineer. It's also important to consider the location of the transformers and the panels. Transformers should be located in a well-ventilated area. It should be protected from physical damage. Panels should be located in an accessible location and should be clearly labeled. All electrical work must be performed by qualified personnel. They should follow all applicable codes and standards. The National Electrical Code, or NEC, provides detailed requirements for the installation of transformers and panels. It also includes requirements for grounding, bonding, and overcurrent protection. It is essential to adhere to these requirements. Ensure the safety and reliability of the electrical system. The installation should comply with all local codes and regulations. This may require obtaining permits. It may also require inspections by local authorities. Regarding grounding, it's important to properly ground the transformer and the panels. Grounding provides a low impedance path for fault currents. It helps to protect personnel from electric shock. It also helps to prevent damage to equipment. The grounding system should comply with the requirements of the NEC. It should be inspected and tested regularly to ensure its effectiveness. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together. It creates an equipotential plane. This helps to prevent voltage differences between different parts of the system. It reduces the risk of electric shock. The bonding system should comply with the requirements of the NEC. It should be inspected and tested regularly to ensure its effectiveness. Now let's review a summary of the steps. Firstly, calculate the total load. Consider the number of stations, the amperage per station, and the potential for continuous loads. Secondly, determine the transformer capacity using the formula kVA equals current times voltage divided by 1000. Thirdly, apply a demand factor based on the operating characteristics of the training facility. Fourthly, select transformers with appropriate kVA ratings, impedance voltage ratings, insulation class, cooling method, and enclosure type. Finally, ensure that the panels are sized appropriately, that they are equipped with the correct overcurrent protection devices. Consider the location of the transformers and the panels. Comply with all applicable codes and standards. Perform grounding and bonding. Remember to consult with qualified personnel. Review historical data or perform a load study to fine-tune the demand factor for better accuracy. Consider the potential future expansion and factor in the growth into your calculations. The NEC mandates adherence to specific safety measures during transformer installation. Firstly, transformers must be installed in readily accessible locations. This accessibility ensures ease of inspection, maintenance, and repair. Secondly, proper ventilation around transformers is paramount to prevent overheating and potential fire hazards. Adequate airflow facilitates heat dissipation. Thirdly, transformers should be protected from physical damage. Barriers or enclosures can safeguard against impact. The NEC outlines stringent grounding and bonding requirements for transformers. Grounding establishes a low impedance path for fault currents. It minimizes the risk of electrical shock. Bonding ensures electrical continuity between metallic components. It prevents voltage differentials. Overcurrent protection is crucial. It safeguards transformers and downstream equipment from damage due to excessive currents. Fuses or circuit breakers must be appropriately sized. The NEC specifies clearance requirements around transformers. These clearances maintain safe working distances for personnel. They prevent accidental contact with energized parts. Warning signs must be conspicuously posted near transformers. These signs alert personnel to potential hazards. They emphasize safety precautions. Regular inspections and maintenance are essential. They ensure the continued safe and efficient operation of transformers. Qualified personnel should conduct these tasks. Lastly, the NEC provides guidelines for the proper disposal of transformers. Environmentally responsible disposal practices must be followed. They minimize the risk of contamination. Here's a breakdown of typical equipment found in a hairdressing training station and their approximate wattage. Firstly, hair dryers typically range from 1500 watts to 2000 watts. Secondly, curling irons average around 50 watts to 150 watts. Thirdly, flat irons generally consume 50 watts to 200 watts. Fourthly, clippers usually require 10 watts to 25 watts. Fifthly, styling stations with lighting may add 50 watts to 100 watts per station. Lastly, miscellaneous equipment, such as timers and small appliances, might contribute another 20 watts to 50 watts. Considering the combination of equipment used at each station, a reasonable estimate for the total wattage per station would be around 1700 watts to 24-25 watts. This range accounts for the simultaneous use of multiple appliances. It provides a buffer for variations in equipment wattage. Based on this wattage range, the current draw per station can be calculated using the formula current equals power divided by voltage. At 120 volts, the current draw would be approximately 14.17 amps to 20.21 amps. This calculation further reinforces the importance of using a demand factor. It helps to accurately assess the actual load in the transformers. It prevents oversizing or undersizing. It's also prudent to provide spare capacity in the electrical system. This spare capacity accommodates future expansion. It allows for the addition of new equipment. It ensures the long-term reliability of the system.